Selamat siang Bapak Ibu sekalian, selamat datang di webinar ASHRAE Indonesia Chapter. Kali ini webinar kita bertajuk tentang district cooling, teknologi dan konsep, terutama kita akan membahas tentang magnetic bearing, centrifugal chiller untuk district cooling. Mohon maaf, mohon maaf saya bicara dalam bahasa Indonesia mungkin ya di pembukaan ini, atau bahasa Inggris boleh Pak Fatur biar berbicara yang lainnya. Terima kasih. Good morning, good afternoon, and good evening. Thank you all for finding the time and joining our today's webinar. My name is Herlin Herlianika and I will be your moderator on this webinar. Our topic today is district cooling design and technology, the design and concept magnetic bearing centrifugal chiller. We will have Mr. Faturrahman Yudi Nugraha, the President of ASHRAE Indonesia Chapter, and Mr. Steve Shah, Chartered Engineer in Energy, Certified Energy Manager, and Accredited Energy Auditor for SP Group Singapore. So make sure you will stay with us for this for their interesting knowledge sharing and best practices. We will also have a very interesting technology update from sponsor for this webinar, Mr. Nicholas Chance, the Deputy General Manager of Applied Product Management from Daikin. Mr. Chan will speak about magnetic bearing centrifugal chiller. I think it will be with HFO refrigerant, yeah, Mr. Chan. Before we start, let me explain how you can talk with us during the webinar. If you have any question during the presentation, please write the question on chat box. We will answer your questions on the Q&A session after the three of our speakers deliver their presentation. If you wish to get answer for one certain speaker, please also mention to whom your question will be addressed. We will have a short break after Mr. Shah for 3 or 5 minutes, so you can grab your coffee or any other refreshment. Now, not to waste too much time, shall we begin, ladies and gentlemen? Our first speaker is the President of ASHRAE Indonesia Chapter, Bapak Faturrahman Yudi. He has, of course, I think everybody already knows, he has experience on product design, especially for chillers, for more than 10 years, including chiller with HFO, with neutral refrigerant, and with all type of technology. So, Pak Fatur, now the screen is yours.
Thank you, Bu Herlin. Thank you for your introduction, of course. Can I share my screen? Okay, thank you. So, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, very good afternoon for you all, the participant. Firstly, I would like to say thank you for the participant on this webinar series from ASHRAE Indonesia Chapter. This is always interesting for us to doing this webinar series month by month and with more interactive and more interesting topic. So in this time webinar, we grab the topic that's district cooling design and technology, and also we will have special speakers for the Daikin, our sponsor this time. Thank you very much for your time and for your sharing. In my presentation, I would like to start the presentation with the standard ASHRAE regulation. So first of all, I would like to read the code of ethic and code of conduct in every ASHRAE event. We will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core value of excellence, commitment, integrity, collaboration, volunteerism, and diversity. And we shall avoid all real or perceived conflict of interest. And ASHRAE is a global organization encourage to all the members to avoid the sexual harassment, and we have special video and special brochure for this case. And also we are very straight about the commercialism in every presentation material. So a brief a little bit about the ASHRAE, that maybe some of you already joined the ASHRAE already, but some of the rest is not yet joined. So our ASHRAE members now is going more and more increase. To all of you that not yet joined the membership of ASHRAE, I would like to encourage you all to please check the ashrae.org/join to join the membership, or also you can check our local website on ashrae.or.id, so we can support you to help if you have any problem with the registration for the membership, or you can send also the email to us at the address info@ashrae.or.id. In this opportunity, I would like to give you a little bit about the kind of membership in ASHRAE. Basically, we have four different type of member. First one is full member. This is according to your experience in HVAC and refrigeration industry, how long you already involved, or how long your experience in that. If you already 12 years more, you can you will get the full members. And then if you still new in the HVAC and refrigeration industry, maybe you can start in associate member. And for Indonesia, especially, we are in developing economy countries. So ASHRAE have the special rate for us. There is $135 for years instead of 230 for the regular rate. And then we can get also from the student the special rate for developing economy like Indonesia is only $15. So this is really worth it to you all, especially for the student to join us in ASHRAE. And then if you already graduate in your university, you can start a job on this side, and then in 3 years first of your job, ASHRAE also accommodate the affiliate member. So starting from the student member, you can increase your 3 years first on the job with special rate, 35, and then 40, and then $70. So this is our also benefit for the economic developing country like Indonesia. So please join. And then when we join as a member, we will get the copy of ASHRAE handbook. This will be free for every year. When we continue as a membership, we can get the ASHRAE handbook. So you will have finally at least 4 ASHRAE handbook completely, from the fundamental HVAC application, system and equipment, and also the refrigeration. Also, you can, if you like, you can also get the handbook online on ashrae.org, handbook online. After that, also in every month, as a membership, we will get the ASHRAE journal. There is many articles, many technology information that will share in the ASHRAE journal. So we will get updating from the world country, for world industry, for HVAC and refrigeration. And of course, we know that our standard is used in many sectors, for the building, for the energy efficiency, and for refrigerant also. We have many standards that you can download. Some of them is free, but some the others is we have to buy some dollar to get the standard. Okay, I will connect our speakers topic. So now I will explain a little bit about the district cooling based on the ASHRAE guidebook. The subject is district cooling guide. This is second edition version in 2019. Since the first edition is 2013. The objective is I will try to give understanding about the district cooling system concept, and then a little bit about introduction of district cooling system main component. So we will start firstly about the district cooling system. So normally district cooling system is talking about distribute the thermal energy in form of chilled water from the chiller plant or the central source plant, and then distribute to any customer as residential, commercial, or institutional, or also the industrial customer. More is used for the space cooling and the humidification, but it is not limited on this application. Of course, you can use also for the process cooling if you like. And then as a historical, the district cooling system is starting in early 1930 in North America, especially in US. And in recent years, in 8 years from the 2009 to 2016, there is growth in America about the using the DCS system. You can see in this right graph. So in 2016, in North America, there is more than 40 million square feet area that cover with the district cooling system. But the interesting one, also in last 8 years, outside the North America also have increment about the use of DCS. You know, as Dubai, as a Southeast country, also Asia Pacific, and also in Qatar, there is many district cooling system that adopted. And you can see this is even higher than the US area. So in 2016, the area covering with DCS is more than 100 million square feet. So this is really interesting. So why people like the district cooling more and more? So I will continue on the next slide. Okay, the potential applicable for the DCS is really interesting, because when you have the thermal load density is high, or the full load hour of cooling is high, for example, in high-rise building, or for the commercial office building or the mall, with the same region or same district, this is very applicable for the district cooling system. And then also, if you have the cooling supply is really mandatory or really high reliability needed, such as the hospital or the school or data center, this is also can be considered to use the DCS system. So that's why maybe if we're talking about the planning, it is better when we have built the new estate of industrial, for example, or the new district for the, for example, our country will have a new city of country, IKN, Ibu Kota Negara Baru. Maybe this will be interesting if we can consider using the DCS. And then, of course, we have benefit from the environment benefit first, because when we use the district cooling system, it will be more efficient. Because what? Because the greater efficiency from the large capacity is better than the small capacity of the unit. So more efficient equipment and also the ability to staging the equipment will be close to match the load. This will be our first benefit. So our energy will be lower than we have the in-building equipment. And the second one, the DCS will take advantage of diversity of demand. So this will be combined, can be combined with the thermal storage application. For example, in some country or in some region, the electric cost in the evening is much more lower than the afternoon. Maybe we can use the thermal storage, something like that. And then the third one, also we can get the benefit on the natural resources. For example, in Europe, there is one district cooling system using river as cooling water. This is called the free cooling. So the condenser of the chiller will be cooled by the river. So instead of the cooling tower that use the fan or the high electricity, they use the natural resources such as a river for the cooling the condenser. Also, this is one state of the art of design of the district cooling. And the fourth one, this is about the refrigerant. So when we talking about the refrigerant, but day by day, everybody will talking about the ozone depletion and also the global warming potential. You can imagine if we have only one big central plant, this will be controlled more easily than we have many chillers spread out in every building. So in this case, we can handle refrigerant in safer and controlled environment. And from the economical benefit also, we can get the benefit from the operating personnel. For example, if every building maybe will spend a team for operating if they have own chiller. But if with DGS, they will eliminate the personnel. So just get the chilled water from the others. And then insurance also not used for the equipment. And then for the usable space, if we have chiller plant on our building, so we can eliminate this the space and we can use space for the others proper. And then maintenance also we will skip the maintenance equipment, and then we will have high reliability and also the higher efficiency. There's the some of benefit of the district cooling system. And then we're talking about the main component now. There is three primary components in the DCS. First is the central plant, and then the second is about the distribution networking. And then the third one is consumer system or interconnection between the distribution and the customer in the building. So you can see the illustration on the right pictures. This is the DCS schematic concept. When we produce the chilled water on the plant, and then we distribute them to every load in the building to the customer. So this is the three main component of the DCS. And on the first component, we're talking central chiller plant. This is what we can use to produce the chilled water. At least there is three options. One is electric driven compression refrigeration. This is a normal one. We use electrical power to favor compression cycle. This is the chiller that we oftenly use. The technology is also more and more go to more efficient. This is the selection of the compression. We know that we use some of reciprocating compressor, for example, and then continue use with the screw compressor, scroll compressor, or even for the big capacity, it should be the centrifugal compressor. There is electric-driven refrigerant equipment. And then the other option, we also can use the thermal energy-driven. This is like absorption chiller. that the main power is using the thermal energy, can use the waste heat or something like that. The third option, we use gas or steam turbine or engine direct with the compression refrigeration equipment. Or we can combine on that technology from thermal energy driven with the electric driven compressor. This is something that we can combine and we can get the best efficiency as possible. And of course, we need also the smart control system when we thinking about the redundancy and also partial load and etc. etc. This is one of topic in the book on the district guidebook. ASHRAE explain more in more deeply. Except the chiller, we have the heat rejection equipment. For example, in this diagram, you can see on the left side of the chiller, there is a heat rejection equipment. It can be cooling tower, it can be evaporative condenser, or it can be also the free cooling like example for the river or seawater. And then the other component is in the side, we use the water pump to distribute the chilled water or to distribute and provide the cooling water system. So in the chiller plant, at least we will have this equipment. Talking about the pump.
Sorry, Pak Fatur, your time is 3 minutes left. Yeah.
3 minutes. Okay, Bu. Thank you, Bu. So talking about the design, in this DCS, the temperature difference is really one of basis design. This is how we combine, how we can find the matching return and supply chilled water from the source, from the chiller plant to the customer. This will be affected to how big the pump. If we have higher delta T, of course we can reduce the pump power because we will reduce the flow rate. But for the other side, if we use higher delta T, this will be impact to the cooling coil on the AHU. So this is also one of basis design and explain more in the guidebook. Pumping system also have optional. When we use many chiller, we can combine it with the, for example, this is parallel chiller with individual pump or parallel chiller with VSD heater pump. Many options that we can choose, and we can select it based on our design. The second component after the chiller plant is the distribution. So this distribution is maybe one of more costly on this DCS, because what? Because the piping will be buried on the ground, and usually this is many structure and construction matter in this installation process. For example, how we insulate them, how we make sure the corrosion is not inside the pipe, and also we can thinking how this pipe can stand for at least maybe 40 or 50 years, so we can get the really reliable installation. And that's why many option now about the material of the pipe, starting from the standard steel, and now we will get many options like HDPE, for example. This is more resist from the corrosion, but there is plus minus about this option of the material. And then the last component is about the distribution, from the district cooling network to the customer. There is two options. One is direct connection and two is indirect connection. What is the difference? The difference is direct connection. It means that from the network pipe from DCS, this will be connected directly to the cooling load on the building. So will be directly go to the HU or to the FU, This is directly without any equipment. And in direct connection, there will be another equipment between the DCS and the building. So we will have a heat exchanger between that. After we get the networking, we will join to the heat exchanger, usually the split heat exchanger, and then on the building circle inside the chilled water, will be connected to the heat exchanger. So we'll have bridging between the DCS and the building load. And there is plus minus between the direct connection and indirect connection. It just depends how we can control it, or how we can more precise on the control. If you have control system that you will play more, maybe better we will choose the indirect connection. And of course, we should have another cost. There is plate heat exchanger that is quite big. And this is about the metering. Also, this is very important, because if DCS provider to you, they should charge to you about how much chilled water you use, or how much energy you use on from our DCS. So this is about the metering the chilled water flow rate, and then you can also add the inlet and temperatures chilled water, or you can use the energy meter to make the clearly how much cost will be charged on the building. This is some comparison between the chilled water flow rate instrument. This is many flow rate flow meter. Sorry, it is many type of flow meter you can use, and with some limitation about the installation. There is 10 diameter, at least up to 40 diameter, for example, and every flow meter have their own characteristic. So hopefully this is a very little brief about the district cooling system, and you can find out more on the ASHRAE guide, district cooling guidebook. If you need it, or you like to design this district cooling system, I suggest to you to have this book to help you to guide of your design district cooling system. Thank you very much for your kind attention, and I would like to back to Bu Helen. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Pak Patur, for introducing ASHRAE standard and knowledge that relate to district cooling technology. It is very interesting, and this presentation, all this presentation is you use from the reference is ASHRAE standard, ya, Pak Patur. So to all participants, please write your question in the Q&A box, and we will answer it in our Q&A session. So please don't hesitate to write down your question and answer. We already see 3 or 4 questions in there. So not to waste our time too much. Also, let's have Mr. Steve Shah to the screen. Mr. Steve Shah leads the business development for district cooling within SP Group, Singapore District Cooling. SDC, a subsidiary under SP Group, provides centralized production of chilled water in the premium district of Marina Bay. Also owns and operates the largest fully underground district cooling plant in the world. With more than 15 years experience in providing sustainable solution and green retrofit for building owners, his team also focuses on the developing energy efficiency solution through district cooling concept and strategies. Steve is chartered engineer in energy, certified energy manager, and accredited energy auditor. Mr. Shah, the screen is yours.
Yep. Okay. Thank you, Helene, Pafato, and ASHRAE Indonesia, as well as Daikin. Well, let me share my screen. Okay. So my name is Steve Sia from SP Group, and I would like to share today, our experience from SP Group in implementing district cooling in Singapore. So maybe I'll start. I'll just give a short intro about SP Group. We are a energy utility company which is operating in Asia Pacific. Right? We own and operate the electricity and gas transmission distribution network in Singapore, as well as part of Australia in Victoria. Now, we are the sole provider of billing and metering services to roughly 1.5 million residential homeowners for electricity in Singapore itself. And SDC, right, Singapore District Cooling, is a direct subsidiary under the SP Group. Now, I think as what Pafato has mentioned previously, district cooling is not a new technology. The International District Energy Association, right, IDEA, has been around for more than 100 years old, right? And around the region, in Southeast Asia, countries like Middle East, Malaysia, Singapore, Thailand, they have also been tapping on such systems, but of course, with a varying degree of success. Now, we need to realize and recognize that there are multiple challenges, right, to implementing district cooling, or DCS for short, right? One, from the construction operations, right, maintenance, the tariff mechanism. How are you going to charge the customers? How are you going to recover back the cost of the capex that you have put into the plant itself? And how do you convince the value of district cooling, right, to the developers for them to take up this system, right? Because it may be something new to them. They are very used to in-building plant having to operate their own system, having to have their own facility management to do their own system, and now they are going with this system, a district cooling system, which may be outsourced to a third party, right? And let the third party run it while they will be paying, chilled water like a utility as electricity or even water. So as such, we do think that, for district cooling to be successful, right, in the country itself, it is critical, of course, to have a partner with relevant DCS experience, which have done other projects before, to go in, to implement such a system. Now, in Singapore, we are providing chilled water to the Marina Bay Financial District. So as what just now Fatou has also mentioned, right? District cooling works very well in areas or in developments whereby you require very high reliability, right? You require a very high quality of water. You need to have a very dense population, a dense thermal district areas. So where in Singapore, whereby the financial district is an area whereby there are a lot of banks, a lot of data centers, there are hotels, there are also even integrated resort, right? And you have things like the casinos are also there. So if you can see on the right hand side, this is where the commercial buildings of One Raffles Quay, One Marina Boulevard, and these are commercial buildings with banks in there. To the left, the iconic Marina Bay Sands integrated resort. So you have the large hotels, the 3-tower hotels. You have Gardens by the Bay itself. Now, our plant, it was a design, build, own and operate contract for 30 years. We started operation in 2006, and we have 3 plants, right, which are interconnected in a network with a combined capacity of roughly around 60,000 tons, 60. right? Providing chilled water to 30 buildings within this area itself. So the plants has been running for more than roughly around 15 to 16 years already. Okay, so for those who are maybe not familiar with a district cooling plant, like a district cooling plant, you can see on the left-hand side, right? This centralizes where the production of chilled water, which is then transported through a piping network, right, to the buildings for air conditioning use. And this is done, with heat exchangers that are located within the building itself. In the Marina Bay itself, the network transportation, what we actually use is what we call as a common service tunnel, right? So we have a tunnel that runs beneath the Marina Bay. This common service tunnel not only houses the chilled water pipes, but it also houses the telecommunication pipes, the lines, the electrical lines, the water and the gas pipelines as well. So all these are embedded into what we call as a common service tunnel. Now, we think the model of design, build, own and operate works very well for district cooling systems. And the reason is because district cooling plants are very large-scale infrastructure projects, right? And thus, considerations for maintenance, even future expansions, future retrofits of the plants are very important factors, right? Which needs to be thought through even at the initial design phase. There are technical challenges, right? Which things like how to deal with part load efficiency, low delta T syndrome, right? That you normally face in a building itself. Even the siting of where the physical plant should be itself are also critical to the success of the DCS plant operations, right? So you need to have really a team that is able to thought through the whole process from the design, right, all the way to how it's going to be constructed, to later on, during the whole 30 years of operation and maintenance, how are you going to maintain that plant? How are you going to, bring in a new chiller, maybe at the end of the 15 or 20 years life cycle of the chiller itself, right? How are you going to transport this new chiller, bring out the old chiller, while not disrupting the operations of the entire district cooling plant itself? Now, let's look at maybe the key benefits of a district cooling plant. Of course, the first key benefit that, having a DCS is on asset efficiency, right? And this, will lead to savings in terms of CapEx and space, right? Basically due to using lesser equipment. A very simple model that I have here. If you have 5 buildings, right? And each building, they are operating one chiller, and you have, of course, one spare chiller itself. Now, if you centralize the plants together to serve these 5 buildings, what you do is that you will be able to reduce down the number of spares, and hence you save on, first of all, cost capex and the space for the plant rooms, the space for the cooling towers itself. And this integration of plants and saving capex, saving equipment is not new, right? We have done multiple studies, and even our national agencies, right, have also conducted a study sometime back to understand what is the state of chiller plants in individual buildings itself. So what they do is they compare the number of chillers that is being installed in the building, as opposed to how much chillers or how much capacity is actually being utilized, right, or being operated on a day-to-day basis. And the conclusion is that an average of 200% spare chiller capacity in each building, right? And what does this mean? This means actually for every one chiller that is operating, you actually have 2 spare chillers sitting there, right, doing nothing. So the potential for savings, right, in terms of space, in terms of equipment, will be very tremendous. if we are able to integrate the plants together. Another key benefit of district cooling, right, is the higher energy efficiency. I think this is something whereby Pak Fato has mentioned earlier on as well. Now, in the district cooling plant, it is very important to have the ability, right, and the controls to consistently load your chillers to close to its design capacity, right, at their most energy efficient loading level. You wouldn't want to, buy a chiller that that gives you or that is able to provide you maybe 2,000 ton, right? But because the efficiency is best only at 60%, right? So you need to operate it only at a 60% level. So in the district cooling plant, we try to use whatever that we have bought, meaning that whatever installed capacity, we try to maximize it fully. Right, we try to make sure that it's operating at its full capacity. So it's very similar to driving a car, right? If you drive a car in a city, you are always accelerating, you are braking, which is very inefficient. But when you are driving on a highway, right, there is very minimal stoppage. Your engine is running at very constant RPM. You'll be able to get a better fuel efficiency. So this is what we are trying to do. In a district cooling, we try to make sure that 80%, 90% of the time, we try to drive on highway. Now, one important factor of district cooling plants, which we, in our case, which we realize is necessary, right, is the use and the capacity sizing of the thermal storage itself. Right, it's a very important consideration during the design phase. We have been able to constantly load and operate our equipment at its full capacity and most energy efficient point, right? Basically through the use of our thermal storage. Now, other than having to be able to charge our thermal storage, at its lower electricity tariff, and discharging them during high electricity tariff rates, right? The thermal storage also helps us to reduce the need, right, to operate any additional chillers, right? And because you have to operate one additional chiller, all the rest of the chillers goes to part load. It prevents such a scenario from happening, right? So many in-building plants, basically they are operating inefficient. It's not because they have been designed to be inefficient, right? It's because that the initial design that the plant was supposed to be running on was not met. Meaning to say, that maybe the plant was actually designed to be operating at a cooling load of 1,000 ton, right? But when when the building is being occupied, there may have been certain changes in maybe even the change of use, the change of tenants, and because of that, the building cooling load isn't what it has been designed to be. It may have gone down to instead of 1,000 ton, it may have gone down to maybe 600 ton, right? And there's nothing much you can do, right? Because your chillers, your pumps have already been fitted in. Although they may be fitted with variable speed drives, but there is also a minimum operating condition, right? That the VSDs or the chillers can also perform. So because of all these changes in the building itself, part load conditions in an in-building plant often occurs, right? And this sometimes play out across the entire building life, right, of 15 to 30 years of the chiller plant before you can replace the next equipment in the chiller plant itself. Now, and of course, because of the way we operate, right, the plant, using thermal storage, having a good design, being able to make sure that it fits into our O&M phase as well. We have been able to consistently outperform many of the district cooling plants around the region as well, right? Now, one key advantage of having district cooling plant is also that it allows better utilization of roof spaces. We have been able to unlock value of roof spaces typically that is being used for cooling towers, like for lifestyle amenities. Marina Bay Sands, right, is one good example. You can see that, in the Marina Bay Sands Resort itself, there isn't cooling towers on the roof, right? And because there aren't any cooling towers on the roof, they were able to construct, and build out outdoor swimming pool, right at the top of the building itself, with a very scenic view across the Marina Bay. Now, of course, district cooling is all about scale, right? And with scale, there is also the ability that you are able to implement very cost-effective, even waste recovery, heat recovery systems that you can harness actually the waste heat from this DCS plant, and recycle them and provide hot water, right, to buildings like for hotels, convention centers, F&B outlets. And this is what we have done, right, for our Marina Bay Sands resort itself. We remove the heat, right, from the resort, right, through the air conditioning. We recover back this heat. We use this heat. We heat up the hot water, and we supply this hot water back to Marina Bay Sands, the hotel rooms. And so, with this in-building plant concept, with district cooling, it has allowed us to venture overseas, right? And we have another project in Chongqing, China, right? With a developer called Capital Land. This again, was a DBOO model, right? A design, build, own, and operate model for 20 years. It involves, two thermal plants, 6,000 RT each, right? So you have total of 12,000 tons there. And it's being used, to serve the cooling and the heating needs of the development itself. And we are providing both the chilled water and the hot water for air conditioning purpose, as well as for space heating purpose. Now, this system has really been in operation since September 2019, right? And it has helped the developer Capital Land to save, almost $30 million in utility costs over the 20 years. Now, we think we can do much more with district cooling as well, right? And, other than just looking at commercial buildings, financial districts, right, integrated resorts, we are also piloting our first residential township using district cooling concepts. And, this, we are talking about an area of roughly around 700 hectares, across 5 residential districts, right? 300 blocks of flats, and it's going to be home to 42,000 households. So you have 42,000 home units over there. And this township, typically it will consist of amenities such as, schools, retail malls, neighborhood centers. And the residential centralized cooling that we are going to be designing for this township, right, is expected to be, at least 30% more energy efficient, right, than the conventional split unit aircon that the homeowner actually uses today. And this centralized cooling system, right, will not only provide chilled water to the residents itself, but also to the commercial facilities within the township itself, right? So you fully make use of the infrastructure and the equipment in the plants itself, right? In residence, you typically use the aircon during the nighttime, right? So what are you going to do during the daytime with all these plants and capacity? So what we do is, we provide chilled water to the commercial facilities, right? To the schools, to the centers, to the retail malls within the township itself during the daytime. And during the nighttime, when all these facilities, shuts down operations, the chilled water is then diverted to these residential units, right? And this helps, to reduce down the overall energy demand, even for the township itself. Right. So centralized cooling, we term it as a centralized cooling system, or CCS, right? Is a smart, eco-friendly cooling technology. right? And that replaces the inefficient split unit air conditioning system. So chilled water, will be generated directly from highly energy efficient chiller plants, which we are going to install them on the rooftop of each building itself. Right. And if you do, a comparison, right? On the left, you have your typical split unit aircon that you use for your homes, right? These are, air conditioning that uses refrigerant, right? And refrigerant is then piped to your fan coil unit. There will always be a condensing unit, that is installed either on the aircon latch or against the wall, right? And with all these condensing units outside of the aircon latch, typically you need to go and do maintenance. You need to climb out of the homes itself to do maintenance on all these aircon latches. Now, these condensing units also adds to the urban heat island effect, right? Because hot air will have to be dissipated out through the condensing units, right? And in the home itself, you can imagine, from the first story all the way up to your 30th story, the condensing units are all stacked up, and that's where, there will be a stack effect. The bottom, the first story condensing unit blows out hot air. This hot air is then, transferred or is sucked into the condensing unit on the second floor, and vice versa, go up to the third floor, fourth floor, and fifth floor. So naturally, the condensing unit, which is almost at the top floor, right, or the 29th or 30th floor of the unit, typically takes in all the hot air, right, and it becomes very inefficient. Now, with centralized cooling, you have your cooling towers, you have your chiller plants all at the rooftop, right? It's very well ventilated. And as we all know, hot air will rise, right? So if you really have your air dissipation cooling towers at the top of the unit itself, it will help to keep the surrounding area within the homes, right, cooling as well. Now, so some of the benefits of centralized cooling system, right? You will have of course quality and reliability, right? Because right now you are having industrialized chiller systems, right, which are able to help you provide chilled water to the units itself. All the homes will be condenser free, right? So you do not need to worry about maintenance issue. Cost savings, right? We talk about energy efficiency as well, right? So these systems, larger systems are typically more energy efficient, right, than smaller systems itself. And these systems, will also have, smart controls. So they are able to monitor, how much you use. And the good thing is, you will be paying based on, chilled water usage. So how much you use, how much you'll be paying for it.
Sorry to jump in, Steve. You have 2 minutes left.
Okay, Ken, no problem. Yep. So and I think one of the benefits, right, that we move from a district cooling to a centralized cooling is on the enhanced system reliability, right? You can imagine if you have your own split unit system, if your condensing unit is down, right, you are not able to provide air conditioning, or your house will no longer have aircon. But if you have a centralized cooling system, right, these are all on the rooftop of the plants. Even if there's a maintenance, one of the chiller is down, because our plants are all interconnected together, they will be able to still provide you cooling, right, to the home. So what you will get and enjoy will be uninterrupted supply, right, of chilled water to your house. Of course, we are not stopping there, right? We have also started to look at brownfield district cooling systems, right? When we say brownfield district cooling systems, we're talking about existing buildings, right? Because majority in Singapore itself, right? At least 80–90% of the buildings are already being built, right? So what are we going to do with all these existing buildings or brownfield? We are looking at what we call as a distributed district cooling, right? This is the project we are embarking, right? And this is on the east side of Singapore itself. We have 14 building owners, right? With their own buildings, operating a combined load of only 9,000 RT, right? But when we did a survey, when we went down to look at their plants, the total installed RT, right, capacity was actually at 22,000 tons, right? So they practically you have one chiller running and one chiller sitting down there doing nothing. So we think that there will be savings in terms of replacement costs, in terms of maintenance costs, and even improvement in the energy efficiency if we are able to integrate all these plants together under a single network. Right. So with that, this comes to the end of my presentation. I have left the contact details, of my colleagues for those who are interested in further discussion. Thank you very much.
Thank you for your very interesting presentation, Steve. So please, everybody, ladies and gentlemen, write down your questions to the Q&A chat, Q&A box, and we will answer your question. We already have more than 10 questions now, yeah. But let's discuss on the Q&A session. I hope you have already your coffee and tea now to continue our next session. Let us welcome Mr. Nicholas Chan, the Deputy and General Manager of Applied Product Manager from Daikin. Mr. Chan will deliver his presentation about the design concept of Daikin HFO centrifugal chiller. Mr. Chan, the screen is yours.
Sure. Can you hear me?
Yes.
Okay. Hang on a second. All right. Okay. Yeah. Just putting up my slide. Okay, thank you very much. Good afternoon, everyone. It's my pleasure to introduce to you a new kind of chiller, the next generation centrifugal chiller running on ultra-low global warming potential refrigerant R1233 ZDE. It's an HFO refrigerant. A two-stage compressor technology is employed to give a very good efficiency. And with that, it's running on totally frictionless magnetic bearing. So 4 main technologies are incorporated in the HFO magnetic bearing chiller. These are some tried and true technology that has been in the market for a while. Revised technology, some are conventional, that is being used in centrifugal chiller nowadays, all across the market. And these technologies are being put together to optimize, to fully unleash the HFO refrigerant R1233ZD to tackle rising global warming. The magnetic bearing technologies that is employed this time in this chiller follow the usual track of frictionless bearing technology. And in the market, right, throughout the last 18 years, there have been various forms of magnetic bearing technologies, such as the small size one that has been launched about 18 years ago by one manufacturer. And about 12 years ago, in about 2010, 2009, more manufacturers came up with their own design of larger capacity magnetic bearing chillers. And I've seen that mainly happening in Americas and some part of Asia, especially like Australia and Singapore. The HFO magnetic bearing compressor, I would say, is rather new in the market and mainly leverage on existing magnetic bearing technologies with some major modification in the impeller aerodynamics, such as the size of the impeller blade geometry, and also most importantly the impeller rotational speed to fully unlock the full potential of the HFO R1233ZD refrigerant that is of low pressure, if you don't already know. So when designing the core components for this chiller, which is the compressor, right, there are mainly 4 focus areas. First, of course, to provide a winning performance, right? It is needed to get back to the basic of research of the aerodynamics of the centrifugal impellers that will work well and, like I say, unlock the full potential of this new refrigerant, right? The R1233ZD. And secondly, right, is we know that friction is the parasite to the mechanical parts movement and would reduce the efficiency. So in order to eliminate that, in this HFO magnetic bearing compressor, a totally lubrication-free and frictionless magnetic bearing is therefore employed. And thirdly, nothing will move, right, if we do not provide it with the most efficient driver, that is the motor. So for this, a long proven tried and true high efficiency motor, which is the permanent magnet motor, is being utilized. And this is especially good for medium to high speed application of the compressor. And lastly, right, in this era, we know that nothing will operate without an intelligent controller brain, right? For this, the control logic has to be reprogrammed so that it's clever enough to modulate the compressor rotational speed and gas flow so that the efficiency can be optimized for all chiller loading. So now let us take a closer look into this technology. So first, let me give you an overview of the chiller with various component layout. Right. So this is a 500-ton chiller that I'm showing. The picture shows the location of the compressor that you can see is with 2 impellers on each side, and the air-cooled VFD are placed in front of the compressor and next to the economizer. They'll see this thing that's standing there in vertical. And one thing that you cannot see from the picture, right, is the I've mentioned before, this is a low pressure refrigerant, right? It's the purge unit. So let me just quickly show you where the purge unit is. The purge unit is here. All right. So since the chiller is running on the low pressure R1233ZD refrigerant, right, there could be non-condensable gases that will enter into the refrigerant circuit, which is common for all negative pressure chillers, such as those that uses this refrigerant, that is the R1233ZD, R514A, or 123, R123, the HFC R123. So the pressure in the evaporator is lower than the atmospheric pressure. The use of this purge unit, right, is to purge out these so-called the non-condensable gases, such as air that gets into the system. The purge unit is like a mini kind of cooling system that provide further cooling to the non-condensable mixture of the refrigerant and air from the condenser. So the refrigerant and gas can condense into liquid and flow back to the evaporator while pushing out the air. So the purge unit this kind of purge unit is quite modern nowadays. It could run in a few modes, right? Manual, auto, or adaptive mode. And in the adaptive mode, the purge unit will self-learn, mostly, based on the duration of time it needs to push out the air. Okay. So after we look at the general layout of the chiller, let us take another deeper dive into the 4 core technology of the chiller that I've mentioned earlier. I would like to show you how each of these technology looks like. We're mainly focusing, like I say, we're mainly focusing the area of aerodynamics, which we want to which we design a back-to-back 2-stage impeller on each side of the motor. And secondly, like I say, that's the lubrication technology, or in other words, the lack of magnetic bearing is utilized, so no lubrication is needed for the HFO magnetic bearing compressor. So it gives a truly frictionless-free operation to the compressor. And thirdly, the driver technology, most reliable and high-performance motor, which is the permanent magnet motor, is utilized in this chiller. And lastly, the controller technology. So 2 of the inlet guide vanes like this, right, is utilized to control the inflow of the refrigerant to the compressor. And also, other than that, VSD is also utilized to modulate the compression speed to meet the building cooling load with the most optimized efficiency. So all these are controlled by the chiller intelligent control logic. So I would like to show a closer look at the compressor, where the 2-stage impeller are arranged in the back-to-back manner on each side of the motor. So by having a impeller on either side of the motor, right, the rotational force and thus the thrust load will be very balanced on the rotor axle and on the bearing. So this kind of design does not put stress on just one side of the compressor drive shaft, like those of the inline impeller compressor, where both impeller are situated on only one side. So this kind of technology is also being utilized in some other form of chiller in the market. There are the oil bearings one, there are the refrigerant bearings. So I would say that this technology is pretty. It gives a pretty good balance to the compressor drive shaft. So and pretty matured as well. So with the advancement of the computing and manufacturing technology, right? Nowadays, the more sophisticated impeller design can be realized. So a 3D impeller blade, also called a three-dimensional impeller, that you see at the bottom right of this diagram, right, has a more complicated blade design, which varies in geometry compares to the straight blade design like next to it, right? Like next to it. So the straighter blade ones are called the 2D impellers. So 3D impeller, why is it needed? It's because the changes in the gas pattern, right, which arise from different compressor loading, sometimes they don't have optimized contact. So you need to design a shape, right, such that these gas flow pattern changes, all right, can have the very optimized contact on the blade surface. And this will improve the efficiency when the chiller go from full load to part load. So with the help of a vast compressor design experience, and also nowadays, very strong computing equipment and very intelligent design software for the aerodynamics. So that allows enormous amount of aerodynamic simulation to find the best 3D geometry, right, that could fully utilize and unlock the potential of the HFO 1233ZD refrigerant. And to manufacture this sophisticated 3D blade with the advancement of manufacturing technology, the multiple axis machine station can be used, and most importantly is to achieve the best cost. So that's why you see centrifugal chiller has been improving the efficiency throughout the last few years and in the future as well, because manufacturers gaining more experience, computing power getting stronger, manufacturing technology getting better. So this pushed the boundary of the chiller design, and in the end, the customer can benefit from very highly efficient chiller. So we'll talk about the benefits of using a truly lubrication-free frictionless bearing. The magnetic bearing, right, is truly lubrication-free, which is more than just oil-free. There are ball bearings in the market, right, that utilize oil or other form of lubrication, such as ceramic bearing that's oil-free but still uses refrigerant as lubrication. So the non-lubrication-free bearing, right, although they are oil-free, it does not eliminate the lubrication system. There will still be additional lubrication line, filter pump, so on, which adds to the system complexity and the potential cause of failure. Also, the use of oil lubrication system will also contaminate the heat exchanger and reduce the heat exchange effect as the oil deposition build up in the heat exchanger over the years. So as shown at the top right hand graph, right, as the oil content in the heat exchanger start building up, the efficiency will drop. And a truly lubrication magnetic bearing system, right, like the HFO magnetic bearing chiller, can reduce the probability of chiller failure and help to maintain the chiller efficiency. But of course, technology, I have to be fair, they come in different prices, different costs. So in the end, it is up to the owner to decide in terms of investment, payback, to see what are their best option, or ultimately the best choice. So let's take a look at the driver technology that are put into the HFO magnetic bearing chiller. So the use of permanent magnet motor, I'm sure most of you would know the benefits, right? However, I would like to say that the use of this technology is a very good justification of investment nowadays, because this permanent magnet motor technology is mature, proven, And the price of the permanent magnet motor has become much more affordable, and it gives the best performance compared to conventional induction motor. The ASHRAE magnetic bearing chiller impellers are directly driven, which does not require any gears. The motor uses VFD to vary the speed of rotation for the impeller. The speed range from medium to high speed, generally in the range of the low thousands, like 2,000-3,000, to the high tens of thousands, like maybe 8 to 10,000. All right. The use of permanent magnet motor guarantees high motor efficiency for most of the speed range. And also due to the magnetic field of the motor is provided by permanent magnet, there's very little torque fluctuation and almost no rotor excitation loss compared to induction motor, where magnetic flux are generated by electricity. This makes the motor reliability of the permanent magnet motor higher than those of the induction motor. Therefore, we believe that the permanent magnet motor should be a very good choice for your customer as well. So and the other thing is with very high power factor, right? Like more than 0.95, the customer would not have to pay for power factor corrector or risk paying more for the electricity. And the chiller is not a complete chiller, right? If it's not equipped with the control mechanism to give the reliable cooling capacity and optimize efficiency. So let me introduce to you the two kinds of control mechanism, namely the inlet guide vane, we call the IGV, and also the variable speed drive. So the compressor is equipped with two inlet guide vanes, all right, one on each side. And on each of the and the IGV is to control the refrigerant flow into the impeller, all right, into the impeller. The angle of opening, right, for the IGV blades not only affect the amount of refrigerant flow into the compression, but it can also affect the efficiency of the compression. And if you look at this, the various dotted line here that I show here, right, it shows, it represents various degree of the opening of the IGV blades. All right. So when we turn the IGV blade to a certain angle, there will be efficiency on the improvement of the compression compared to IGV blade that is fully open. So when it's fully open, right, I put a baseline like there's no efficiency improvement. Okay. For example, at this 30% load, right, if we change the IGV opening angle from the green line to the yellow dotted line, right, you see a slight green line and a yellow dotted line here. The efficiency can improve from about 2 to 8% compared to the IGV blade that is fully open. Why is that so, right? It's because when the refrigerant are being pre-swirled, all right, pre-rotated before it enters into the compression by on the impeller, right, it could help with the efficiency improvement. Although, by doing so, we could optimize the efficiency by changing the IGV opening angle, right? So at what angle the efficiency will improve, it really depends on how you design the compressor. So different degree of opening give you different degree of efficiency improvement. And there will be a point, right, like this 30% load that you can improve up to 8% at certain angle of opening. However, by doing so, right, it also affects the amount of refrigerant flow. Therefore, the capacity will be altered if you play with this IGV blade opening angle. So how to control the capacity, right? That's why a VSD has been put in to accurately control the amount of compression, right, to meet the required cooling capacity. So you see, you need the IGV and you need the VSD, both working simultaneously to get you the right cooling load and the best efficiency. So by combining this, you could achieve both, right? Get the right capacity, get the right efficiency that you want. So in order to do that, a lot of simulation need to be done. All right, a lot of computing need to be done. And I still go back to where I started to say is with the advancement of today computing technology, right? Computers are able to run a lot of simulation to find the most optimized IGV opening angle and VSD speed. And most of us are engineers here. Once you found out this empirical formula, you put that into the chiller controller, so that the chiller controller will be smart enough to utilize all this simulation result, right, to control the impeller speed and also the IGV angle to get the best efficiency at the right cooling load. So other than the four main core technologies that was put into the compressor, a efficient heat exchanger also needs to be designed to be used with the ASHRAE R1233ZD refrigerant. So most of the R1233ZD chiller in the market, right, they're redesigned to meet the to fully utilize the new properties of this 1233ZD refrigerant. So and most important thing is we know that the R1233ZD refrigerant, right, it actually costs a lot more than the R134A. Generally, if I were to give you a number, right, about maybe 4 to 6 times more in terms of price. So by redesigning the heat exchanger into one that utilizes less refrigerant, such as the hybrid falling film heat exchanger, where the refrigerant are sprayed onto the heat exchanger coil tube, right, it can reduce the refrigerant charge up to 30–40%. All right, compares to a flooded heat exchanger. So flooded heat exchanger is whereby the heat exchange copper tube are immersed, in a pool of refrigerant, and moreover, the refrigerant distribution system is also been enhanced into a multi-stage kind of refrigerant distribution system, where the refrigerant are first evenly distributed onto a distribution plate. Then after that, right, is sprayed onto the heat exchange copper tube. So to further enhance the compression efficiency of this two-stage multi-stage compressor, a vertical economizer is utilized. How does this economizer works, right? The economizer allows, right, the separation of high pressure flash gas from the liquid refrigerant through a cyclonic effect, for this vertical economizer. So what happened is the high pressure liquid refrigerant from the compressor will first go into the economizer from the top side. All right. So as it flows down, right, it will be flowing down in a cyclonic manner and circulating the wall of the economizer. And the economizer will be equipped with a mesh-like feature, mesh-like wall. So the high pressure liquid refrigerant as it's moving down the wall, right? The pressure and because of the pressure change, right, some of the liquid refrigerant will flash into high pressure gas, all right, while some of the high pressure liquid refrigerant will be trapped in this so-called mesh-like wall, all right, and the liquid refrigerant will be collected at the bottom of the economizer tank, and of course it's sent back to the evaporator. So while the refrigerant the flash gas, right, will be carried up and exit again from the top of the economizer and sent to the second stage of compression. And because this high pressure flash gas is not doesn't need to be compressed 2 times, right, but only 1 time at the second stage impeller. So with this economizer, it could save the compressor more work, and if that's why the efficiency of the chiller can be further enhanced. So all the aforementioned features, right, are utilized to so-called to elevate the performance of the ASHRAE magnetic bearing chiller. So let us look at the result. So we have done various design, actually, other than the ASHRAE magnetic bearing chiller. We have also looked at, actually there are various designs that we have designed using the oil bearing, using refrigerant bearing. We call it the other ASHRAE chiller that we have looked at and we have designed but not launched. So how does the ASHRAE magnetic bearing compressor compares to other form of ASHRAE chiller using other technology that we have previously designed but not launched, right? So in this case, right, I'm showing you an Australia scenario where the ASHRAE 2-stage magnetic bearing centrifugal chiller is brought into comparison with other similar HFO chiller that we have looked at, all right, in our company. So in this example, right, I'm showing the efficiency in kilowatt per ton. Okay, in kilowatt per ton. So just to have some more clarity is that the lower the kilowatt per ton, the better. All right. So Australia design are usually with lower chill water temperature at around 5 to 6 degrees C. So this design, right, is slightly higher, has slightly higher lift compared to the ASHRAE condition. So in this example, if you look at the graph, right, the HFO two-stage magnetic bearing centrifugal chiller has outperformed other form of HFO chiller that is by around 7 to 11% in all load under condenser relief situation. And if we move on to this in a Singapore actual scenario, where the HFO two-stage magnetic bearing chiller is brought into comparison with other form of HFO chiller. Singapore design are usually have higher chill water temperature of around 8 to 8.5 degrees C. So this design is slightly lower lift compared to the ASHRAE condition. In this example, if you look at it, right, the performance improvement is about 4 to 6%. So my objective of showing you this, right, is not to really to highlight how much better, right, the two-stage HFO magnetic bearing chiller is comparing to other form of HFO chiller, right? But I want to show you that the two-stage design with magnetic bearing is very good for both low and high lift situation, and especially good for high lift situation. And this why is needed, right? Because we know that in the emerging Asia market, the ambient is higher, and like Indonesia, Malaysia, so on and so forth, right? So and in most cases, the chiller will operate at a higher lift situation. That's why the two-stage technology with the magnetic bearing is very suitable for a high lift kind of application. And the HFO, why we want to have the HFO magnetic bearing chiller is actually to have a more sustainable chiller for today's and tomorrow's need, right? So let's take a further look at that. So a while ago, I mentioned that the HFO magnetic bearing chiller does not need a lubrication system. So here on the left-hand side, you see that the HFO magnetic bearing chiller is very simple in design compared to the to those that needs the lubrication. Those are on the right-hand side. So that's why a truly lubrication-free system is more sustainable in long-term use because it breaks down less. And without oil, the performance can almost be maintained close to the original performance. But of course, fair to say that, you know, normal scheduled chiller maintenance will still have to perform as well. And without the need of lubrication system, the maintenance cost of the chiller will almost be consistent as year goes by. So in this accumulative line, you will see, right, the blue line. So those with major overhaul will need that needs to be done on the lubrication system, which could involve motor teardown, filter change, lubrication system check, so on. You know, we incur higher costs every few years. So which make the cumulative maintenance increase in a more exponential-like manner. So as for footprint, right, the HFO two-stage magnetic bearing chiller is, I wouldn't say that it's the smallest in the market, you know, but it's, I would say it's pretty optimized. So in this case, for the, say, the example of a 500-ton chiller, you see that it's about average in width compared to other form of HFO chiller. And some side is slightly shorter, some side is slightly longer. But I would say, you know, I would generally say that the size is pretty reasonable. I wouldn't say that it's the smallest, it's reasonable. So as for the operating cost from the chiller comparison example that I've shown in the Australia case, right? The HFO magnetic bearing chiller has overall lower operating costs when we compare it to other form of you know, HFO chiller that could be using the lubricated bearing, single stage. This shows here on the right-hand side, graph on the blue line. All right, so the saving over these 10 years, right, is about close to about 100,000. So does that saving justify, right? So let's take a look at the next page. So in this page, I've shown the initial investment cost different compared to HFO chiller of other form. The HFO, to be honest, that the HFO two-stage magnetic bearing centrifugal chiller, right, is about 20,000 USD more expensive for this case, roughly. All right, that's why in the beginning I said that, you know, other form of chiller, they although in terms of efficiency wise, it could be lower, or there are other form of downside, but you know, there are definitely, you know, technology come with a price. All right, and in the end, you know, the justification is you know, is been decided by the owner. So from this case, the saving, I mean, with the saving of slightly less than 8,000 USD a year, right, 7,000 something, the payback will be less than 3 years. So this means that the from third year onwards, building owner will be able to make a net savings when using the HFO magnetic bearing technology. So this is generally, I would say, that is in line with the market expectation of 3 to 5 years. And lastly, yes.
Your time is only 1 minute left.
Oh, sure.
Yeah.
No problem.
Okay.
That's my last slide. So the objective of using the HFO next generation chiller is really to help humanity in combating the global warming. So according to our analysis, is that a chiller will contribute to global warming in 2 ways: direct emission and indirect emission. So the HFO bearing magnetic bearing chiller with ultra low global warming potential of 1, right, almost does not contribute to global warming through direct emission. Also, a two-stage HFO magnetic bearing chiller can almost surpass, you know, the efficiency of the HFC chiller in the market. So with a 2% improvement on the HFO bearing magnetic bearing chiller over the other HFC chiller, right, the global warming potential contributed by direct emission of HFC chiller can be totally offset. So which means every HFO chiller you are putting in, right, you are helping the market to offset those HFC chiller that is already installed in the market. However, you know, environmental concern, I know, is not the only consideration of the owner. So there are also initial investment costs, availability of refrigerant. So in the end, I guess it is our job as you know, including all the listener who sells you know, chiller. I guess it's our job to really, you know, provide a good analysis and advice to our customer. You know, whether the HFO chiller is their choice. You know, ultimately the decision is by them, right? All we can do is we give a good, you know, technical analysis to them. All right, thank you very much. Thank you.
Thank you, Nick. It is
Thank you.
very interesting. Yeah, actually, some of you maybe already know a bit about this technology on the ASHRAE CRC last time. Yeah, Nick. This time you have more detailed explanation about this technology.
Yeah.
So
thank you.
Yeah, thank you, Nick.
All
so
right.
let's have a Q&A discussion now. Wow, we have already 29 questions. It's great, but I hope we can manage to answer the questions. Yeah. Let's go to the first question from Mr. Lenovo. I don't know who is this Mr. Lenovo, but for speakers, please see all the questions. If you can answer it by texting, so please answer, because we don't have much time to answer each of questions. So I will start with the first question from Mr. Lenovo. I hope we can have a name from Mr. Lenovo. Mr. Nicholas Chan, I have questions about R1233 refrigerant. Is refrigerant negative pressure type, all right? If negative pressure, can you explain about purging issue?
So I believe I've explained through my discussion just now. So there's a purge unit like every negative pressure chiller would have. So basically it's to purge out the non-condensable gases like the air. So how it does is the purge unit will run in a few modes. It could be manual that you set, every purging every few hours. Whether whether when the chiller stop, it could be purging if you set certain time. And it also with nowadays, I think it's quite standard in the market of the purge unit. To be fair, I think most manufacturer they buy the purge unit from a third-party supplier, and it's pretty intelligent already that it could learn right from the chiller like when it needs purging, and it will learn a trend by adjusting its own timing of purging out the air. So I would say generally it is there's no issue in purging out the non-condensable gases through this or the purge unit.
Okay, thank you, Nick. For Mr. Lenovo, if you still have questions, please put write it on in the Q&A, so Nick can give you further answer. Yeah, Nick.
Sure.
Second one, I will not read the second one from Mr. Jason first, but maybe I will start with Mr. Jordan Simanjuntak. What type of development will be suitable for district cooling system to be applicable as per Indonesia ambient? Maybe this question will address to Steve, yeah, Steve or Pak Fatur. Maybe Steve first, yeah.
Yep. Okay. Thanks for the question. I think just now we were really talking about the type of developments, right? For district cooling, typically you look at those which have very high thermal density, right? Places where developments that has banks, financial districts, they have data centers as well. If it's an integrated resort or a hotel, right, they will be, of course, very suitable for district cooling. But I guess the other way that we are looking at is we do not want to only have one specific kind of building development in that area, right? For instance, you do not want to only have commercial building, right? Because that may also mean that you only have cooling between your 9 a.m. to 8 p.m. right? If you include in overtime hours and everything, so you only have cooling between that time. You want to have a good mix of buildings, right? But typically, you want to have some which may have hotels, right? You may also want to have retail malls in there, so that you Saturday, Sundays, the weekends, the malls will be filled with people. Cooling load will also be high, and that is how you then utilize the chillers to its fullest potential, right? I'm sure Nick's chillers are meant to be running, constantly. Are meant to be running 24 hours, only down for shutdown. They are not meant to, only run 12 hours of the day, right? It doesn't make sense to build a chiller, to build equipment that is so expensive, but you only utilize it for only half of the day itself. Yeah. But I think in Singapore, what we consider as a very good kind of a building that can go for district cooling is one that has a plot ratio of above 12 or 15, meaning that is a high-rise building, right? Because the cost of running the pipes, the chill water pipes, right, as what just now Fandu has mentioned, is going to be expensive, right? So you want to have a shorter distance of pipe that needs to be run from the plant to the neighboring building, and within the building itself, that is where the typical riser pipes can be run. Chill water pipes can be run. So you want it to be high rise, right? And so that you will have larger load in the building itself. Yep.
Thank you, Steve. Pak Fatur, you want to add?
Yeah, maybe a little bit additional from my side. According to the challenge of hot and humid like Indonesian climate, this is actually, in my opinion, is not really disadvantage. But I think this is only also we can see it the case in Middle East, for example. Middle East is really have very high ambient temperature. So when we use district cooling, even more we can get more efficient or saving. We get more when we use the district cooling. system. So anyway, in Indonesian character of developing is maybe this is one of our gap. So we really not really easy to use the district cooling concept in our country because not many district. For example, in Jakarta, we can you can see SCBD in Sudirman, maybe one of example that we possible to doing the district cooling system because there is many high-rise building, many commercial, many mall, and also the hotel. But if we can see, there is not many district area like that. But in the future, if we developing in this direction, maybe district cooling will be one of the option solution for us to make an efficient system. That's my additional value.
Yeah, thank you, Pak Fatur. Nick, maybe you want to add also something?
No, I'm good. Thank you. I believe the two experts have answered most already. Who am I to talk, man? With the two experts in there. No. I'm good. Thank you. I'm happy. Thanks.
Okay, Nick.
Thank you.
Let's go to the next question from Pak Pepen. Pak Pepen is from Ministry of Public Work. The question is addressed to Steve. From your experience in Singapore, what is the problem of your direct district cooling system? Steve, please.
I think maybe it is not really a problem, right? But it is the changing of the mindset, right? For building developers to give up their plant, right? Whereby traditionally they have always been, having their own FM guys managing the plant. They are so used to having the control over the plant, right? When are they going to run the plant? When they're going to stop the plant? When they're going to do the maintenance of the plant? And now you have to change the mindset such that the plant no longer belongs to them. They are only going to take chilled water, right, from them, and it becomes like a form of utility, right? As I say, like like electricity, like gas, you buy as per use. So the changing of the mindset, I think, at the moment is most difficult, right? Because the guys have been so used to doing the same thing over and over again. Some of them maybe are even so used to hearing the sound of the pumps, right, running just beside their office. And suddenly you take this whole system away, you park it outside their building itself, and you just supply them chilled water. Yeah. And of course, the challenge is that for them, they have to then incur this cost as an OPEX cost, right? Because the chilled water, regardless of you paying for it, right? There is some cost that is involved in the capex, which typically in a building itself you will have already paid upfront, right? When you buy the chillers, but right now you are not buying the chillers. You save the money upfront, but you are paying it through your chilled water bill. So that is the change of mindset, and the change of maybe even the accounting practices that they will have to adapt to. Yeah, but this is slowly changing, right? So in Singapore itself, we started off in the Marina Bay. We have roughly around 30 buildings, who have already come on board. There are, we have 2 or 3 more districts which are also going onto this model, right? District cooling model. Yeah, so that is coming on, but it took us almost 10 years, right, to convince building owners to come on board with us, right, and to change the mindset.
Yeah. Thank you, Steve. For Steve, Fatur, and Nick, please answer Pak Edi Saman question with type your answers, yeah, because the question is very simple about the pilot project of this district cooling in Indonesia. I will move to question from Pak Jordan Simanjuntak. What type of development will be suitable for this district cooling system to be applicable? Maybe this question goes directly to, oh, it is already answered, yeah. We will move to Pak Nur Hadi Andoyo. The question addressed to Stephen. Steve, it is interesting, Mr. C. It's opened my mind about the conventional installation of chilled water system with district cooling system. Can you show the number cost of efficiency between the two of system? I also see the simplify that every top of building could be explored widely. Steve, it is the question is for you.
Okay, I think in terms of the efficiency, I would rather say the cost savings, right? In Marina Bay itself, we have seen and we have showed to the building owners, right, that across the entire life cycle of their building itself, which we talk about roughly is around 30 years, they will see cost savings of from between 15 to 20%, right? Life cycle cost savings, and of course, they have a upfront cost that they will have already saved because they no longer need to put in their chiller plant, right? What they do is they only pay for the heat exchangers, right, in their building itself. So opposed to having their own chillers, cooling towers, these costs are all saved upfront itself, right? Second, of course, in the Marina Bay itself, land is very expensive, right? The land value is a premium, right? So when you are able to save this land, you are able to utilize it for other purposes, right? For whether commercial, residential, or retail. The land is put into more better use, right? And it allows you to have a better yield, right? Rather than you have it as a chiller plant itself. So overall, we are always talking about roughly around 15 to 20% savings, right? In terms of energy efficiency, we have seen most plants, right? It will degrade over the years, right? And basically this is because, once you install a plant, you don't change the chillers as often as, you change other items, right? You typically take a 15 or 20 years chillers, leave it there for the next 15, 20 years. But in our plant, because we started off, there is always an expansion requirement, right? When with the new buildings coming in, we then we add in more chillers, we add in the latest chillers, we add in the more high efficiency chillers. So every 6-7 years we add in newer, more efficient chillers. So our plant, instead of degrading, actually in our Marina Bay plant is actually improving, right? We are getting more and more energy efficient as the years goes by, right? So for instance, what I can share is, right now our 15-year-old plant, the efficiency is actually better than what it was at 1 year old, right? Then we started at 1 year old, basically because in between we have brought in more chillers. So that's the the advantage of having a district cooling plant, right? You don't install everything all upfront, right? But you make sure that your plant is able to have expansion capacities, right? That means you make space available, you have the planes available for new chillers to be brought in, right? To increase your cooling capacity, to increase your install capacity, as and when new buildings are coming into the network itself. From there, yep.
Thank you, Steve. Now we will move to question from Pak Tadi Sutandi from Polban. Pak Tandi is a lecturer from Polytechnic Negeri Bandung. The question is addressed to Nick. What happened if the magnet system failed to operate? Any anticipation from the chiller, or need to wait the maintenance to come and check the unit?
Yeah, I'm actually typing this answer. I'll just answer it here. All right, so far in my 10 years of looking at the various magnetic bearing chiller from various manufacturers, I have to be fair to say that I've not seen the magnetic bearing system fail. All right, many brands I've seen, no. Generally, the failure comes from the VSD, not the magnetic bearing. But if it fails, yes, the chiller will stop to operate. and maintainers will have to come and check for sure.
Okay, then you can continue to from question from Pak Dedi Rasid. Pak Dedi Rasid is our senior in ASHRAE Indonesia Chapter.
Yep.
The question is how is the minimum load for this magnetic bearing can achieve, which will maintain the high efficiency?
Sure. Different magnetic bearing chiller under various conditions, they do have different unloading. I would say that for generally from a multiple magnetic bearing chiller point of view, all right, the unloading is 10 to 20% in constant condenser. All right, a single magnetic bearing chiller, I would say that generally it is about 20-30%. All right, in some cases, if operation allows and is at the sweet spot of the compressor, it could go down to about 10 to 15. So, but to be safe, I would say that, around 20, for single, and for multiple, maybe around 10, 15. Yeah, but situation dependence, of course.
Okay, thank you, Nick. Let's move to the next question from Pak Premi Raymond Agustinus. The question is for Pak Fatur and Nick. How much an efficiency rate in power consumption kilowatt per ton rep we get when we install the magnetic bearing chiller compared to the conventional chiller? What about the comparison of this price, such as 2 times or more expensive, or how is it? Yeah, please,
Okay.
Nick, go and Fatur. After Nick, continue with Fatur. Yeah.
Sure. So generally, from the theory of magnetic frictionless, is we are talking about 1 to 3%. All right, from the point of without the friction. All right. However, I also have to put in context is that magnetic bearing chiller comes in many forms, and the most popular form is a multiple compressor magnetic bearing chiller. When we talk about performance improvement, it is really from the part load. So the full load, 1 to 3%, without the friction. Part load wise, a magnetic bearing chiller that comes in the form of multiple magnetic bearing compressor, all right, versus a conventional oil bearing chiller for which most of the market has only a single compressor for less than 1,005 ton. The efficient improvement can be huge. Like we are talking about maybe 10 to 20%, not because of, well, I would say that to be fair, it is because of magnetic bearing, and it is not also because of magnetic bearing. Why is it because of magnetic bearing? Because magnetic bearing compressor comes in small capacity form. That's why it can have multiple compressor in a chiller, and that benefits, right, the part load operation, the huge improvement over a conventional chiller that usually come in bigger compressor form that, in many cases are single compressor up to 1,000 or 1,005 tons. So, we cannot only look at magnetic bearing, right, as the only form of performance improvement. All right. Yes, frictionless. Yes, it helps a bit, but the efficiency improvement is also due to the market availability of this magnetic bearing compressor that is in small size and also in multiple compressor configuration. So it's commercial point of view and also technical point of view. Yep, that's my answer to that.
Okay, I will add something from answer to the question. Typically, as I know that magnetic bearing compressor centrifugal chillers have really good kilowatt per ton, especially in partial load, as Mr. Chan explained here on the slide. This is can achieve even 0.3 or 0.4 on the partial load. If we compare to the conventional centrifugal chiller, maybe just 0.56 kilowatt per ton, roughly. So this is the benefit of the magnetic bearing centrifugal chiller compared to the conventional. So on the 100%, maybe it's just a little bit different, maybe 0.5, 0.5 something, but on the partial we will have a huge benefit when we use the magnetic chiller centrifugal. This is my additional action.
Thank you, Pak Fatul.
Yep.
Agree. Yep.
Thank you, Nick and Pak Fatur. Next question that I would like you to answer. This is the question for Nick from Rahmat Apandi, Ucap PT Arya Jaya. We have 4 questions. Actually, you can see yourself. Nick, is HFO 1233 ZD safe for use? What is the pressure of evaporator? Is HFO chiller more expensive than HFC chiller and so on? Yeah,
Okay.
actually it is similar question. Yeah,
Yes.
but yeah, this I will consider that it is done after you answer this question. Yeah.
Right. Yeah. So I answer this or
yeah.
Okay, okay.
You can
All
answer.
right. So it's safe to use. It's A1 refrigerant, so neither flammable nor toxic. All right. Pressure is lower than atmospheric pressure. I think it was 60 something psi on the evaporator when it's running on ASHRAE condition. And is it more expensive? Okay, this is a good question. I'll give you an indicator. If you take away the refrigerant, efficiency to efficiency, say both HFC and HFO chiller could achieve, say, very high efficiency of 6.7. The cost of the chiller should be the same. All right. What is more expensive is the refrigerant. The refrigerant is more. The refrigerant price could affect a few percentage points or even up to 10% price on the overall chiller. However, you also have to take note that with most of the HFO chiller in the market, they can achieve a efficiency that no HFC chiller or the old chiller can achieve. So if I'm doing a high efficiency of 6.7 that can be achieved by both HFO and HFC chiller, it is doing the HFO chiller unfair, because the HFO chiller could reach 7.2, 7.3 that at ASHRAE condition, that HFC chiller cannot achieve. So it is more expensive because it can get a higher efficiency that most of the HFC chiller in the market cannot get. And because of the refrigerant as well, it makes it more expensive. But nowadays, I would say chiller manufacturers don't sell the chiller just based on, oh, it's a new product, you know, I got to charge more. No, we work, I guess everyone here, you know, works on, you know, a common sense is that payback must be justified, because we are smarter customer now and we are smarter seller now. Thank you.
Thank you, Nick. Next question from Pak Martua. To Nick, understand magnetic bearing really rely on stability of power supply. How to prevent the issues if there is unstable power supply, and how would be the warranty in terms of unstable power supply? Thank you. Please,
Understand that
Nick.
magnetic bearing really rely on stability. Yes, yes. How to prevent the issue? Actually, if the power supply is really unstable, right, it could really possess a issue to the magnetic bearing. So however, there's way to mitigate. Say for example, on one of our chiller range, I won't mention the name anyway. There's a compressor by our own. It has a ride-through features that even if the power supply is stopped for 10 seconds, all right, I think it was 10 seconds, can't remember, 10 or 15, I'll just be conservative, 10 seconds. If there's a short power loss, it will still be able to ride through that. So if it could ride through 10 seconds of power shortage, power drop, you know, less than 10 seconds of power fluctuation, it will be able to ride through, and the compressor will be able to coast through that power fluctuation.
Okay, Nick, I hope this can answer the question from Pak Martua. Let's get back to Pak Lenovo. I don't know who is Pak Lenovo here. Can you explain, it is for Nick, can you explain once more about purging issue? The signal is too bad.
So, okay, so the purging issue, right, is really because of the non-condensable gases that is trapped in the condenser. So the because the pressure of the evaporator is lower than outside, right? So air will get into the system. What happened is as air get into the system, so what problem it will give? It will be blocking it will be all accumulated in the condenser. That's why it's called non-condensable gases. It cannot be condensed, and it will trap the condenser heat exchange surface. So the heat issue happen is when you don't get enough heat exchange, your chiller will have issue. It could run into high pressure and it will stop operating. So when this issue happen, right? If it does happen, all right, and say the purge unit is stopped for so long that that the chiller heat exchange surface on the condenser is not getting enough heat exchange surface, the chiller will trip stop. And what you need to do is there must be something wrong in the purge unit, right? So you fix it, purge out the system when the chiller is not operating. By the way, the chiller, if it is stopped, right, the purge unit can also be working to purge out the air. So every time you can set the controller to purge, even during the operation or when the chiller is not operating, or like I said, the adaptive mode. So as the air is purged out, the chiller will be free into running again. Okay.
Thank you, Nick.
Thank you.
Yeah. So still, Pak Lenovo, why still using negative pressure? Because when it is late.
Okay.
Yeah.
Why negative pressure? That's a good question. Because HFO chiller, the most efficient refrigerant that is available now is R1233. That is safe, A1. It gives a very close efficiency to even those that is our HO refrigerant, R11. All right, R11 is very efficient. Also the band HFC R123. And the 1233 HFO, that is global warming potential of 1, safe to be used, A1, suitable to be used on large capacity system. There is only one refrigerant now. That is 1233. It's the only choice. It's a sensible choice. And we have seen so many negative pressure chiller in the market. You know, it hasn't been a problem. So yes, we are bound by choice, but we optimize the chiller according to the best choice available. Other refrigerant, they are either positive pressure, not so good efficiency, you lose capacity, and it is not safe, not as safe, all right, that it could be slightly flammable. So I would say that we are bound by the availability of what is the best available in the market. That's our reason.
Okay, thank you, Nick.
Thank you.
Yeah. The next question is from Pak Tuan Kiang to Stephen. How to find load profile of the complex building use district cooling effectively? Steve, please answer this question.
Okay, so I guess, you know, when you talk about the load profile, right, the cooling load profile, in Singapore, how we do it is, you know, we run a E20 simulation software, right? And that helps us to plot out the profile of how the building is going to be, right? And if let's say you have a complex building, a mixed development, you know, of, you know, retail and commercial, residential, then what you do is, you know, you plot out individually, and you then integrate them together, right? And to get the diversification of the load itself. So we typically use simulation softwares, right? You input in all the parameters like your, you know, your ETDV, your occupancy rate, the amount of fresh air that you need to come, you know, into the building itself, your ventilation rates, and with that, you know, you will be able to simulate out a cooling load, what the building actually requires, right? Over the 24 hours from there. So you know, and let's say if for data centers, then it depends a lot about how much equipments that you're going to put into the data center itself. What is the space requirement? What is the humidity requirement that you need? And we use that and simulate out cooling load profile, right, from the E20 software.
Okay, thank you, Steve.
Yep.
Next question is from Ahmad Alatas, PT Policipta Multidesign, to Pak Fatur and Nick.
Sorry, I'm looking for the question. Ahmad Alatas?
Ahmad Alatas, yeah, I lost the question actually. I lost the question.
I see
Come.
a question maybe for Steve is what I'm looking at is from Ahmad Alatas is, are there specific infrastructure that need to be in place for district cooling to be implemented? Is that the one?
Oh, Pak Fatur already answered by typing there. Yeah,
right.
I think.
Okay. There's another question, Rahmat Apandi. Do you want me to answer that?
Yeah, please.
Okay, is the HFO chiller can do rapid restart? Yes, it can. However, I have to be very honest, is that we are testing that. All right, it looks pretty good. But of course, we need to have that. It is not yet officially launched, but yeah, we are testing that. Thank you.
Thank you, Nick. Maybe we move to Pak Deti questions. Please advise until what scope of work responsibility of this PS provider work is the hex and pump inside the property is under the scope of this provider. Maybe this addressed to Steve, yeah.
Yeah, so I think the scope of work responsibility, if let's say we have the heat exchanger, right, in the building itself, typically it will cover from the district cooling plant, right, all the way to the primary side of the heat exchanger. Then, you know, from the secondary side, whatever that is going up to your AHUs, it will then be covered by the building owner themselves, right? But of course, you know, we have also seen various models, like, you know, in our project in China, in Chongqing, the developer preferred that we cover all the way up to the airside equipment, right? So we take care of the water side as well as the air side. So it is not fixed in stone, right? That a district cooling service provider can only, you know, take responsibility up to the water side. We can also, you know, go from the water side all the way up to the air side as well. And there are a lot of variants in this kind of arrangement. Yeah, so it depends on, you know, a lot of how comfortable is the developer, right, with us taking over his equipment itself.
Okay, thank you, Steve. Next question is from Pak Aritian Susanto. Do we still need annual shutdown, Nick?
Yes, of course.
Okay.
Of course.
And then the next question is from Pak Ilda Ismail, PT Aquanin. Are the specific infrastructure that need to be in place for district cooling to be implemented? Ilda Ismail. The question is for Steve, yeah.
Yeah, so I guess maybe if we talk about specific infrastructure, right? I think as just now previously, Pak Fato has also mentioned, one of the key challenges of a district cooling plant, right, is, you know, how to bring that network, the piping network, over to the neighboring building or the building that is going to be taking up the chilled water, right? Often, you know, it may have to run across roads, right? Or if worse still, if the building itself are situated, you know, in a slope or undulating kind of conditions, right? You have buildings on higher ground, some of the buildings on lower ground. How to deal with that, right? So, you know, and one of the easiest way whereby we did was, you know, in Marina Bay, I mentioned before, you know, was the design of a common service tunnel, right? So you have a tunnel that provides all these utilities to the building itself, right? And you know, you then run these pipes along inside these tunnels to these buildings, right? And this tunnel will connect to all the buildings. Alternatively, we have also seen, right, developments, what they do is, certain developments, they may be building, there are some developments in, in Thailand, right? They built 7 towers, okay, 7 office tower, plus retail malls and everything. And they have, and at the bottom, they have a basement car parks, right? And these basement car parks actually run to all the buildings itself. Now you can then use these basement car parks as the infrastructure, right, to run your pipes to these buildings itself. Yeah. So minimally, you need to have, a set of infrastructure or space that is able to connect to all these buildings that you intend to provide district cooling to. Yeah.
Yeah, thank you, Steve. Next question, maybe from anonymous attendee. What are the pros and cons for single stage and dual stage compressor? Nick.
Okay.
Yeah.
I would say generally, two-stage compressor, the pros is of course higher efficiency at high lift. All right. Single stage compressor do not tend to perform so well under high lift. Some people might not agree, but that's my experience so far. All right. The benefits of a single stage is that it is a simpler system. Mechanical, you cannot run away from simplicity. All right, single stage, less bearings, if some that use bearing, right, or magnetic bearing, less of that, less nuts and bolts, less impeller. It's a simpler system, and in some case, maybe it is even slightly cheaper. It depends on how this chiller manufacturer price the equipment. However, having that, is that a problem? If it is is that a benefit? Where both single stage or dual stage are very reliable already. What if single stage is even more reliable, but they all can do a life of at least 15, 20 years, and they also don't break down as often? So sometimes I advise my customer, is that needed reliability needed? They are both very good, very reliable, very matured. All right. Other thing is both single stage and dual stage are common. I could answer that is that when you're doing a data center application, all right, a high living chill water, low lift, it almost doesn't matter whether it's a single stage or dual stage system. When the lift is not that high, both can give you very good efficiency. And some might argue that single stage higher efficiency because there's not so much pressure loss, or the same efficiency, right? There's not so much pressure loss within the refrigeration system, the piping inside the compressor. However, my experience tells me that multi-stage clearly gives a slight better efficiency over single stage. Thank you.
Okay, thank you, Nick. I think we will come to the last question to answer, and we will answer all your questions by email, or you can read the answer on the ASHRAE website. Last question for you, Steve. How is the HFO chiller is applicable or impact to the green building regulation in Singapore?
Is this for Nick, the HFO chiller?
I think yeah, it could be for me, but it could also be for you because you are the owner, right?
Yeah, it is for green building regulation, because it is for green building regulation.
Yep.
From owner point of view.
Okay. Yes. So then in the case, maybe let me start first, right? So I guess for the green building regulation, we recently, or maybe I think start of the year, right? There are NEA, right? Our agency itself, national agency itself, have already stipulated that from 2022 onwards, new chillers that has to come in, right? Anything above 300 ton, it has to be HFO chillers, right? You can't bring in your R134A chillers, or R123 chillers anymore. It has to be HFO chillers. So the industry is moving towards that. There are also incentives, right? There are given for building owners who want to replace their equipments from a HCFC chiller to a HFO chiller as well. Yeah, so the government definitely is encouraging HFO technology, HFO refrigerant, right, and chiller technology as well. So we are all going into that direction. I think Nick has really talked about advantages, the higher efficiency of these chillers, right? And that's where I believe our government have also recognized that these are all moving in the right direction, right? They just need to give a little push to the industry, right, by providing some sort of minimal incentives, right, to move them all into the right direction. So it's more like a carrot, right? The stick will come later when they have to enforce, making sure that there is no more, HCFC coming in. And when you have that, right, the refrigerant, I would think that, the refrigerant, you have to top up refrigerants, right, for your chiller plant. The price of your HCFC refrigerants will also get more and more expensive, right? Because you will have lesser and lesser HCFC going around. Right, so in the long run, it will be parity, right, between your HCFC and HFO refrigerant price as well from there. Yep.
Okay, Nick, you want to add?
Okay, I think eventually, I wish I have to be from customer perspective. All right, although I'm trying to sell HFO chiller, but I think it's only fair, right, that not everyone as rich as Singaporeans. All right, that we can afford that. So there are still customer whose initial investment is important. Sometimes some may think that a 10-15% premium or 30%, whatever, maybe I'll just put a number, 10-20%, a low increment of HFO over HFC chiller. Yes, 3 to 5 years payback justify, but that 10-20% price increase, is it something that your customer can take? All right, some countries, a lot of countries, HFCs still could go on. All right, and their efficiency, I wouldn't say is bad as well. There are very high ones, like I say 6.8, 6 point, even close to 6.9, some of them. And the HFC is not going into a ban, but phase down, although ban could be coming. All right, but it depends on your customer, whether they can fork out their investment. If money is not an issue, then sure, go for HFO, But I know a lot of your customer, money is an issue, and money has always been an issue. But will HFO chiller get better? Of course, because that's the future direction. Because almost no new development or major development will be done on HFC chiller anymore. HFO chiller will be the future, and HFC will definitely go out. It's just at this moment, whether your customer has that money to pay and whether they could take, that HFO refrigerant is not so readily available. But of course, there are many HFO refrigerants. Some are slightly flammable, some are not. Some are better efficiency, some are not. So yeah, but if only for environmental sake, yes, go on HFO. If money not an issue, availability not an issue, it will definitely give you the best efficiency. I'm speaking on behalf of, if no one complains, it's all manufactured in the market. HFO chiller, best efficiency. Thank you.
Okay, thank you, Nick. That's all Q&A that we can answer today. I believe we cannot certify you, but you can still reach the speakers and their teams for further discussion. And I would like to invite Pak Fatur to make some closing remark, maybe Pak Fatur. Please, Pak Fatur.
Okay, thank you. Okay, everyone. Once again, I would like to say thank you to our speakers, Mr. Steve and Mr. Chan, for your presentation. It's really interesting, and I believe this is useful for us. It is so by so many questions raised in the Q&A. So hopefully everybody have some knowledge today. And once again, on behalf of ASHRAE Indonesia Chapter, I would like to appreciate for your all attendance up to now. Now we have 300 more participants. This is pretty unbelievable. And of course, thank you very much. And again, I'll close this webinar series and see you on next webinars. Thank you very much.
Thank you.
Good afternoon.
Thank you very much.
Thank you.
Yeah.
Yeah.
Goodbye,
Bye-bye.
everybody. See you on
Goodbye.
our next webinar. Bye.
Goodbye.
Thanks.
Thanks, Tristan.
Bye-bye.
Bye. Mr. Steve, thank you.
No problem. Thank you.
To all participants, you can find the presentation on the ASHRAE website. Yeah. Thank you.
Modern buildings. At the heart of its cooling is its chiller. The evolution of building technology demands better cooling ideas. Revolutionary ideas, which starts from the drawing board. We asked a series of what-ifs when we designed our next-generation chiller. What if there is not one, but two impellers on both sides of the motor? What if the drive shafts were frictionless? What if the motor were the most efficient? What if there were two compressor modulators for both gas flow and compressor speed? We took 4 technologies called quadrology, fully optimized with HFO R1233ZD refrigerant to give you the WMTC chiller, going above and beyond, redefining chiller technology, maintaining ecological balance, surpassing others at a justifiable expense, to go above and beyond other HFO chillers. We go back to the basics of what makes a good chiller. WMTC. And it's how revolutions begin. Modern buildings. At the heart of its cooling is its chiller. The evolution of building technology demands better cooling ideas. Revolutionary ideas, which starts from the drawing board. We asked a series of what-ifs when we designed our next-generation chiller. What if there is not one, but two impellers on both sides of the motor? What if the drive shafts were frictionless? What if the motor were the most efficient? What if there were two compressor modulators for both gas flow and compressor speed? We took 4 technologies called quadrology, fully optimized with HFO R1233ZD refrigerant to give you the WMTC chiller, going above and beyond, redefining chiller technology, maintaining ecological balance, surpassing others at a justifiable expense, to go above and beyond other HFO chillers. We go back to the basics of what makes a good chiller. WMTC. And it's how revolutions begin. Modern building.